stickler for anything, it's a detail that irritates me. He'll always put a tilde or something over it to indicate it's in the phasor domain. It's in the phasor domain if it's got any imaginary component at all. That's the way I deal with this one. So if you wanted that phasor current, it would be what? It would be this voltage, A, at some angle theta, and it would be divided by R plus J omega L. You all agree with that? Now that's a complex number. It's got a real and imaginary part. So I can render this as simply equal to some I naught, right? Put a magnitude there. And it would be E to the J, and the angle would be the actual angle of I. Right? Because this has a magnitude of square root of R squared plus omega L squared, and it has an angle of inverse tan of omega L over R. Do y'all follow me? So this angle right here is not going to be that angle. Do y'all follow me on this? I'm just trying to be as clear as I can and move you along. All right, now, this is in the phasor domain. When I want it in the time domain, I would say the I of t is equal to the real part of E to the J omega t times the phasor component, times I phasor. And I'm going to expand on that. That means my I of t here is equal to the real part of E to the J omega t, and then I has got some magnitude of I naught that I don't really care about, times E to the J angle of theta I. Now,
when you set up that circuit, you didn't use RMS values, right? You just took the maximum value of the circuit.
right here, it's irrelevant. You could assume peak, you could assume RMS. Doesn't matter at this point. It's usually peak. All right. The reason it's peak is because I'm relating that A to the magnitude there, so it's peak value. Okay. All right. Back to this. Now, if you take a look at this, I'm going to combine some terms, and that means this is going to be equal to, I can take the magnitude of I naught out, because that's strict real, and then it's going to be the real part of E to the J quantity omega t plus the phase angle. I'm just going to call it theta I. All right, so how do I get the real part of that? There's one very important relationship we have to know as engineers. We have to know this one. These are Euler's identity. You remember that E to the J theta was equal to cosine of theta plus J sine of theta. Right? This is one of the three. There's also I could also put down what the sine is and cosine is in terms of exponentials, but this is a real important one. So E to the J theta is cosine of theta plus J sine theta. Here, I have E to the J theta, right? Omega t plus. So I could expand that, and I could say this is actually I naught times the real part of, and then it would be cosine of omega t plus theta, right? Plus J sine of omega t plus theta. Theta I. Y'all follow me on this? I only did this for one reason, because there might be somebody in here who misses this occasion. When it says real part of something, this is strict real, the cosine. This has a J in front of it. Y'all see that? That immediately tells you that has no real component. The real part of the J term is 0. Follow me? So this is the only component that lasts, which means that my I of t for this one is just equal to the magnitude of I naught times cosine of omega t, and then it's the phase angle of the current. Now that's the way an engineer would solve this problem. It's assumed it's steady state. There's not like a switch that goes. Otherwise, we'd have to get the transient component too. But y'all remember this right here? How many remember doing this kind of stuff back in the day, circuits? Thing Dave Irwin, and I guess when I taught it, I didn't do enough of, is making sure you understand this is the original problem. This is the way we solve it to get the magnitude and the angle. Then we go back the other way to get the time domain. That's the observable domain. Follow me, everyone? Okay. So That's phases, but in a nutshell, the real thing that I've gotta say is, whenever we have phasor quantities, we use that relationship to go from real to imaginary and vice versa. And let me just put this up here. So, if you take a look at this, if I have, in the time domain, if I have b dt, in the phasor domain, it brings out a j omega. Y'all follow me on this? I'm just making sure you see that. That's the one thing that happens. And the linkage is always, if you have a time domain quantity, say v of t, it's always going to be the real part of e to the j omega t times the phasor domain quantity v. That's it. That's the relationship that gets you back and forth all the time. All right. Now, why did I say that? Because I'm going to solve these equations, but I'm going to solve them in the phasor domain, not in the time domain, or in the time harmonic domain, would be another way for it. So, take a look at this for a second. Here, pay attention to this and write this down. So we start by first using these to couple, and I want only two quantities left when I'm done. I want E and H. So I want to get rid of J, I want to get rid of B, I want to get rid of B. Y'all follow me? So when I do that, I can say that curl of H is equal to J. Well, J is sigma E plus the partial of B with respect to T. Well, B is equal to epsilon E, so it's plus, really. And I'm also going to go to the phasor domain, so this derivative brings out a J omega. You all see that? Time derivative? So this is going to be plus J omega epsilon times E. Or, better yet, I can say curl of H is just equal to sigma plus J omega epsilon times E. So I took the first equation, and now I've got it completely into the phasor domain, and I've replaced D with epsilon E, and J with sigma E. Got me, everyone? Next, I come over here, and I say curl of E is equal to, well, it's minus dB dt, right? The time derivative is replaced by J omega. Follow me? Then, so I get minus J omega. Then I replace B with mu H. So that's minus J omega mu times H. And these are the two equations I'm going to now work with to get a single equation with one unknown. Y'all with me? Now follow, this is the trick. This is something to keep in the back of your mind. This is something that's going to happen all the time in engineering. We find a clever way to manipulate equations and get rid of variables. And whenever you're talking about either curl equations or derivatives of any type, you always look for some way to make one equation become the other. Now look at this. If I take another curl of this bottom one, so I'm going to take curl of E, that's equal to minus J omega mu times curl of H. Y'all agree with that? I didn't say this explicitly, but I'm assuming that sigma and epsilon and mu are not spatially variant. If they were spatially variant, I couldn't do this. Then you would have to take the curl of the quantity, right? You would have either sigma times E or something like that, and that's a much different kind of thing. Then they break up into several parts, but I'm assuming that mu, sigma, and epsilon are all constants. Follow me? All right, now, this one, why did I do that? Somebody knows. Why did I do that, besides to aggravate you? Take a look at the curl of H. See anything up here that looks as similar to curl of H? Like that, maybe? So now, if I replace that curl of H with this, I have everything in terms of E. That's what I'm going to do. So I have curl of E, curl of E, is equal to minus J omega mu times curl of H, right there, which is minus J omega times curl of H up here. it's equal to sigma plus j omega epsilon times E. Take a look. You see, now I have one equation with just equal. I've got constants in there. I've got sigma, I've got epsilon, I've got mu, but it's one equation with only one unknown. Y'all follow me? All right, next we do a vector identity. We'll try this. So this is an identity. You didn't have vector calculus. They used to require it. I feel bad that you haven't, because most of the stuff you would have seen many times before. So the curl of E is actually rendered as the gradient of the divergence of E minus del squared of E. That's a vector Laplacian. That's what this becomes. That's equal to, and then we do something on this side. Now I'm going to introduce a constant to try, so I don't have to keep writing all these terms right here. I'm going to say this, that gamma is now equal to the square root of j omega mu times sigma plus j omega epsilon. And that's gamma, and that's equal to alpha plus j beta, by the way. Now you had this at the end of your EMAG 1 course. It was in chapter 5. I'm going to remember that. All right. And it's something you're getting reacquainted with. You'll use it all the time. This is called the propagation constant. Alpha is the attenuation constant. It's the actual units are Napiers per meter, and beta is considered the wave number. That's radians per meter. By the way, if you're looking at that and saying, well, wait a second, you can't add things with different units. A Napier and a radian are the same. Okay. All right. A different word. Napier is used because it's attenuation. Radian when it has to do with an angular measurement. You all follow me, class? So now I get down to this point, and I come over here, and I say this is really minus gamma squared. A little better. Minus gamma squared times E. Now we're working our way down to a solution of this that's useful and not something that's impossible to solve and understand. So when I get to this point, I look at this divergence of E, and I've got to do something. I got to get rid of that if I want to solve this thing and make sense of it. So divergence of E, if you remember this, divergence of D was equal to rho V, right? I'm going to remember that. What is that called in a nutshell? Now let me think about that. What's the integral of d dot ds over a closed volume equal to? The charge inside it. You all remember that? Gauss's law. This is the point form of Gauss's law, the differential form. The other form is the integral of d dot ds over any closed surface is the charge inside. Well, this is the differential or point form of that same law. It's Gauss's law. But what we're going to do here, we're going to say we're in a charge-free region. So we're assuming charge is effectively it's negligible. For instance, if we're talking about wave propagation, here where we're standing in this atmosphere, rho v is 0, about 0. It's the same way in deep space. It's the same way anytime you talk about propagating waves, almost always you can assume rho v, or the charge density, is 0. All right. Now, what does that mean? Well, since d is epsilon e, it means divergence of E would be equal to rho v over epsilon, and that would be 0 also. And you can see I have divergence of E right here. Take a good look. Y'all follow me? So when I make the assumption it's charge-free, I can get rid of this term. Now things are looking better. I've gotten rid of them. Now I'm going to get one equation with one unknown. I'll do it over here. I'm trying to write it high so y'all can see it. By the way, are you having any luck recording this? Okay, outstanding. Maybe I'll do it right here so you can actually see it. Alright, so when we take a look at del squared of E minus gamma squared of E equals 0. Only thing I did is I took this del squared of E with a minus sign, take it to the other side. Y'all with me now? Now I have one equation, one unknown, and I've assumed it's charge-free. Now herein lies a problem. In general, you don't need to write this down, just appreciate what I'm telling you. in general, the E field, for a general solution, it would have some EX, AX, you don't need to write this down, plus some EY, AY, plus some EZ, AZ, if we're in Cartesian coordinates. Y'all understand? Generally speaking, there's three field quantities. When I take a look at this in the del squared operator, well, del squared of anything is second derivative with respect to x squared, plus second derivative with respect to y squared, plus second derivative with respect to z squared as the operator. When I take that, look at the E field now. Del squared times E. 9 terms come out of that. Y'all follow? You're going to have derivatives of x, y, and z on both the EX, EY, and EZ components. 9 terms come out of that, and somebody would expect you to solve that. It's an impossibility. You need a computer to solve that. Matter of fact, you wouldn't solve it in the true sense. It would be simulating the solution by approximating the derivatives and stuff. So what do we do here? Well, now we talk about something that we're going to look at called plane waves. Before I put this down, I have to explain something to you. In a way, I'm going to draw from an analogy. If I drop a pebble into a puddle, you'll see ripples come out, right? And they'll come out in a circular fashion. The circles will get larger and larger, and the amplitude will go down. But it'll keep growing and growing and growing, ideally. Think of those ripples in the height as a field quantity, moving, right? Now, if I get far enough away from where I drop the pebble, all of a sudden, it looks like the radius of curvature is going to an infinity. All of a sudden, they look planar. Do y'all follow me on that? They look like they look like basically it's just a wall flowing that way, right? A wave that has no curvature. So when we talk about plane waves, we're talking about being so far from the source that creates them that they're virtually all in the same plane, or you might say that they don't vary in terms of any kind of angular movement. If I could walk up and down the E field wave, so to speak, there'd be no change in actual magnitude. The only thing would vary with is the radial distance, or in our case, the distance, we're going to use Z, because he does in the book. Y'all follow me? So, when we talk about plane waves, we're going to assume the E field itself, will only have an X component, so it will be in the AX direction only, and will only vary with Z. And I'll just tell you the solution. It's going to be some E naught and be E to the minus gamma Z. So it's only going to vary with Z, that's like our radial distance. And it's only going to be something that has an X component. Remember, the electric field has a vector sensitive. You know how the height of that wave could be thought of analogous to an electric field quantity, right? The electric field. Now it's propagating only in that direction. So the E field's in this direction, it's propagating in the Z direction, right? Propagation. The direction of propagation can never be the orientation of the E field or the H field for propagating wave. So I take a look at this, and now I can solve it. I basically solve it. So this becomes the second derivative of E with respect to Z squared. That's the only thing that's going to vary with is Z minus gamma squared, and I'll call it EX, of EX equals 0. Wentworth's book does this. We could do it with a Laplace transform. You can get an assumed solution there. You can assume EX has the form of some constant AE to the lambda Z, and then solve it for lambda in terms of gamma, and you'll get this. You'll basically get the solution to this. Will have two components, and it will be EX, write this down, is equal to some E0 plus E to the minus gamma Z plus E0 minus E to the plus gamma Z, and it will be in the AX direction. Now, I'm going to make a comment. Write that one down. This is important. That's the solution to that equation, with the assumption we're talking about plane waves. We're a long way from the source, and we have only one field component for the E field. Now, when I come down and do this, these are two possible solutions. This one is a wave traveling in the positive Z direction, and this one is traveling in the minus Z direction. So we put a minus there in terms of that E0 minus. Now, this is a direct analog to, if you remember, transmission lines. when you got the solution for the voltage on the transmission line, you had one, you might say voltage waveform moving to the right, another moving to the left or in the opposite direction. That's the only thing here. Same exact equations. Gotta tell you one other thing about this. If you wanted to go to the time domain, and I would multiply this by e to the j omega t and take the real part. I'm gonna do that right there. Here's what you get. If I said, I'm gonna go ahead and get e as a function of z and t in the time domain, it will be ex. That's the real part of e to the j omega t times that quantity. I'll just call it ex. What you'd end up getting is this. You're gonna get E naught. And remember, gamma is equal to alpha plus j beta. So you get this e to the minus alpha z times cosine of omega t minus beta z. And then you would get, and that's E0 plus right here. Then you would get plus E0 minus times e to the gamma z, that's positive now, times cosine of omega t minus or plus beta z. This waveform right here is time, if you let time move on and you replot this, it's showing a wave going in the plus z direction. You do the same thing and replot this one, this is a wave going in the minus z direction. Now, when I say that, you should at least have an appreciation for this. If this is this wave right here, this waveform right here, and this is at, say, this is versus z, if I took it at t equals 0, it would look like this, approximately. There'd be some decay, but that would be about what you get. Y'all follow me? You let time go past, take a millisecond, microsecond, or nanosecond, something of the order of an angular change here of less than 5 degrees, and here's what you get. What you'd see is this thing appears, think of the crest moving to the right or in the positive z direction. All right, y'all with me? Now you've had this in physics, they explain it in different ways, but if you actually plotted this versus time, replotted the waveform, let time increment, you'd see this whole wave, this crest is moving this way. The whole thing would be moving that way, that's to the right or to the positive. If you did the same thing for this one, you'd be going the opposite direction. Y'all follow me on that? And that's as easy as it gets. So from that, now I'm going to talk about something, think of a surfer on the tip of this thing, basically riding the crest. How fast is he moving? Well, that's the phase velocity we get next. So, and I know at least one person in here just heard me talking about phase velocity yesterday. I think, where are you? There you go, yeah. Because he's in a different class than mine. So phase velocity is interesting. We're going to look at phase velocity in terms of this waveform right here. And matter of fact, let me erase that. I just want to focus on this because I want to get phase velocity and wavelength out of the way. Even though you're supposed to know, I know better that some people may have forgotten. So if I have any quantity, we're going to use the E field quantity. We're going to assume it's lossless. It's E naught times cosine of omega t minus beta z. And we can call, it doesn't matter the orientation. This is a standard time variant, time harmonic wave. So this is the phase. Now remember I said for that surfer, if he's on the crest, we start at t equals 0, right? Then the argument of this would be 0, and then I let it increment in your mind, sort of a mental exercise. You can see the crest moving. So how fast is that moving? Well, this is the phase in here. If you're talking about riding the crest, the phase stays the same. So that means if I take a derivative with respect to the phase of that waveform, I would get simply omega minus beta times dz dt. You with me? Taking a time derivative on both sides. But if you're riding the crest, it means the phase doesn't change, so it's 0. Now, dz dt is like anything else. The x dt, dy dt, it's a rate of change of the position, or it's the velocity. So I can say that now, when I have the velocity, beta times the phase velocity would be equal to simply omega, or I can say the phase velocity, which is my dz dt, is equal to simply omega over beta. And that is the phase velocity, and always will be. How many remember that? If you don't remember exactly, you at least seen it before, it rings bells, right? You remember this to a point where there's nothing new under the sun. And you should have a good handle for that because you have a background, you've had your physics courses, math courses talk about this. Now you're having engineering, so you're getting this thing beat over your head. Sort of like integrations with the integral of x dx. That one, you don't even think about. You know it's x squared over 2 plus some constant. Same way with this stuff. It's going to become second nature to you. That's phase velocity. But another thing that comes out of here is wavelength. Y'all following? Now, if you think about wavelength, let's do it this way. Let's freeze time. Let's let t equal 0, and let me plot this right here. So that means my waveform I plot would be E is equal to some E naught, right? And then it would be just cosine of minus beta z, because I'm saying t0, right? All right. Now, how many know what an even function is versus an odd function? An even function is what? If I have f of x, it's the same thing as f of minus x. If you have a function f of x is absolute value of x, that's an even function. If you have f of x equal x, that's an odd function, because an odd value is exactly equal to in magnitude and opposite in sign, an even value. So, this is an even function, cosine, which means I can just make that cosine beta z. I don't need to worry about the negative sign. Y'all following? I couldn't do that with a sign. Now, when I plot that, what do you know happens? If this is plotted versus z, and I take a look at the magnitude of this on this axis, well, at 0, this is 1, so I just have E naught. And then I would get this. And it would be a kind of a periodic waveform like that, right? Y'all with me? Again, time is irrelevant. We froze time. The wavelength is always the distance, or the distance over which the wave repeats itself. It's called the period if it was in the time domain. Here, we're in the spatial domain, so this is wavelength. So how do you figure this? Well, what was the argument of the cosine back here? It's 0, right? 0 times beta is 0. Cosine of 0 is 1. 1 times that is E naught, right? When's the next time it goes to that value? When the argument of the cosine is 2 pi, right? Every 2 pi, you get the same value back, right? So that means I can get this wavelength by saying beta times the wavelength equals 2 pi, or the wavelength is 2 pi over beta. That always works. Doesn't matter if you're in a waveguide, anyway. So that's why you get wavelength and phase velocity. Now, I'll say this too, as an added note. Phase velocity for any wave traveling in free space in an unbounded media is the same thing as the velocity of energy flow, or group velocity. However, when we get to waveguides, and waves are bouncing around, then the phase velocity can be quite different than the group velocity. Keep that in mind. Because the phase velocity itself would have to do with this imaginary fictitious point of intersection of the wave and a wall. For instance, I mean, if you assume a wave is coming into this wall at an angle like this, there's going to be a point where the crest hits, right? And it moves, as you think about it. However, as this wave starts hitting the wall almost normal to it, if for a small change in distance on the wave's crest, there's an enormous distance in change on the actual phase front there. That's considered, it's likened to the phase velocity. All right, it's an imaginary thing, but yet mathematically it is a constraint, and you'll see this when we deal with waveguides. All right, but I'm just bringing that up. So now, more fun. Now we get into the H field for the same thing. So, I mean, I think you've had this in EMAG 1 at the end of the course, but I really don't know how it was presented. So, we've got the E field down, and for a propagating wave, anytime you have an electric field, you have a magnetic field. You all follow me? So, If I think about this, I know I have an E field equal to some E naught, and we're only gonna talk about a positive Z going wave, E naught as such, and it's gonna be times E to the minus gamma Z in the AX direction. So it's propagating the Z direction, but it's oriented in the X. Now, I go back and I say, I know the curl of E is equal to minus J omega mu times H. Follow me on this, guys? So I take a look at that, and what do I see? Well, the curl of E, I don't want to do this, if I take the curl of E, the way I get it, it's Cartesian, AX, AY, AZ, huh? And then it's going to be ddx, ddy, dz, and then you have ex. Since there is no ey, it's 0 and 0. That's the definition of curl of E. It's in the back cover of your book if you've got it, and you don't remember that. But we'll be using curls and divergences and del squareds all the time from here on out. So when I take a look at this, well, the curl of that is ay times ddz operating on ex, and it would be minus ddy times ex, since there is no y variation, 0 in the az direction. So that means this thing is actually equal to ddz of my ex term. And now I do it. When I take ddz of that, of the ex term, I have ay times, so it's an ay direction, and then I'm going to get minus alpha times E naught plus times e to the minus gamma z. I simply took ay times ddz of that, and I got that. And you can see one thing from here. Now you can see the H field itself that you're going to get, this is for a positive traveling wave, will be of the form of gamma over j omega, and it's going to be times mu, and then you're going to have E naught plus times e to the minus gamma z, and it will be in the ay direction. Now, make a long story short, when I take a look at this term right here, that's going to have an interesting thing. If I take a look at j omega mu over gamma, that's actually going to be a ratio of E naught plus to H naught plus. I'm trying to fit this in this lecture, so I'm going to take a second to explain this in a little more detail. But this term right here, well, that's j omega mu over gamma. Well, gamma is equal to, gamma is square root of j omega mu times sigma plus j omega epsilon. Y'all remember that? Now take a careful look at that just for a second. When you take a look at this, I have j omega mu over square root of j omega mu. Y'all follow me? Write this one down. Make sure you write this down. This means I can simply say square root of j omega mu over sigma plus j omega epsilon. And we call that the intrinsic impedance of the media, or eta naught. You can call it just eta, call it eta naught for now. Eta naught, and that is really a ratio of the electric field magnitude over the magnetic field magnitude in the media. Now here, the way I have it, I actually have the H field equal to E naught over eta naught times e to the minus gamma z in the ay direction. E and H are always related for propagating waves by eta, and eta is simply the intrinsic impedance of the media. I think, those people out there. All right, do y'all follow me on this, class? All right, one last thing. We got eta there. Yeah, I will tell you that, let me just state this again. Eta naught, or the intrinsic impedance of the media, is equal to the ratio of E naught plus over H naught plus is equal to the square root of j omega mu over sigma plus j omega epsilon. But I wanna say one other thing. If you looked at the ratio, I won't have time to prove this, of the field quantities flowing in the other direction, or the negative field, the field quantities E minus and H minus, you would find out that the ratio of E zero minus to H zero minus is actually going to be equal to minus eta naught. It'll have a negative sign in front of it. And it has to do with the actual sign here, when you do the curl. Alright, that will come out as negative when you have a positive going waveform, but for a negative going waveform, it's positive, so it'll come out positive, and you're gonna get two different signs. That's the reason for it. And now, how much did I not get to? Okay. Got that, I went through phase, went through wavelength. Hey, I'm happy. Where we're gonna pick it up when we next meet is gonna be in section 6.3, propagation of dielectrics. I'm gonna give you some homework. I know it seemed like the class flew a little today. I had to get through the basics, the phaser stuff, all the stuff you've seen before. I'll slow it down when it gets a little more complicated, but all this should be pretty much, maybe not that right there, but a lot of this should be things you've seen before.
Will we have a quiz on Friday?
Not this Friday, not this Friday. We'll start the following week, okay? And one other thing too, I will send you all a link, and I get it from you. And if you can, I try to get a page, a Facebook or GroupMe page. You guys can handle that, right? GroupMe or Facebook?
Yeah.
All right, and the reason is that way you can interact. You can ask people yourselves questions, talk about the class, do whatever you want. Can't hear you. What? Can't understand.